Okay, so last time we talked about the proximal operators. So let's review the definition of the proximal mapping. Given the function h, we define the proximal mapping associated with h at x as the following as the solution to the following optimization problem. Is hz regularized by a quadratic term. So in particular, we showed that if this h is an indicator function of the constraint set, then the proximal mapping reduces to the projection onto the set. And then we have checked this proximal mapping of the L1 norm, which promotes sparsity to the solution. So if H is the lambda times L1 norm, then the proximal mapping is the so-called soft thresholding operator. And this operator basically it will filter out all those coordinates with small magnitudes. And then for the other coordinates, the operator will simply subtract those coordinates by lambda. And there are some basic properties associated with this proximal mapping. For example, if the function f is a affine, is a linear, is an affine transformation of another function g, then their proximal mapping has the following relation. So proximal f equals to proximal mapping of alpha times g, a times g. And so all these properties can be checked just by definition of the proximal mappings. Just writing down definition, and you can easily show this equivalence. And there are some cases where we are looking at functions of this form. So f is another function g plus a quadratic term. Now, for such a function, the proximal mapping is given by the proximal mapping of g weighted by this constant 1 over 1 plus rho, and then evaluated at this point. And moreover, if f is given by another function g composite with an affine transformation, then this is the relation between their proximal mappings. So for example, we can look at the quadratic addition. We can look at this one. And the proof is straightforward. We just write down the proximal mapping of f. In this case, f equals to gx plus this quadratic term. So by definition of proximal mapping is the minimizer of this optimization problem. Right? It's a quadratic term plus fz. And this entire thing, this is fz that we defined in this example. Right? So you plug in the definition of proximal mapping. And here should be arc mean over z. I think this is a typo instead of x. Okay. And the rest of the steps is to Now, because here we have two square terms, so we can try to complete this square term, combine these two square terms into a big one by introducing some constants and reformulating the problem. So for example, for this line, we expand these two quadratic terms and okay, and then z square we have is 1 over rho plus 2 times z square, because we have one coming from here and the other one from this term. And there's a cross term. We can put them together, and then we have g times gz. Okay. There are other constant terms. For example, we will have some x square and a square terms. Those are constants, so they can be ignored because they do not affect the minimizer. We're looking for the minimizer. And then for this, in this expression, the first two terms can be completed into a big square. So what we do, we just divide everything by 1 plus rho, okay? And then we complete this square term. So in the end, we get this big square term. Okay, so we get this big square term plus 1 over 1 plus rho times g of z. And this falls into the standard definition of our proximal mapping. So this is the proximal mapping associated with this function. And then the mapping is evaluated at this point. Okay, so that's why we end up with the final expression. So we can follow this idea, and we can easily prove all the other properties. And these are some additional properties. Well, we are looking at fx, which is g function composite with a affine transformation, g of q times x. Well, Q is an orthogonal matrix. Now, for such a case, the proximal mapping of F is Q transpose times the proximal mapping of G evaluated at Qx. Again, write down the definition of proximal mapping and do some linear algebra, we can show this. And if there's another, there's an extra offset term plus b, and we can show that, so the expression becomes even more complicated. Okay, so the proximal mapping of F can be expressed in this way, with regard to the proximal mapping of G. Yeah, and sometimes the function is another function of the L2 norm of the variable. So the input to G is a scalar. It's the L2 norm of the vector x. In this case, the proximal mapping of F is given in this form. It's the proximal mapping of G at this point, multiplied by the unit vector associated with vector x. And this property can be proved again by following the definition of proximal mapping. So we start from the definition. This is the definition of proximal mapping of of f associated with f. Now f z is given by g function g evaluated at L2 norm of z. And for the quadratic term, we just decompose it into 3 terms. Now, here is the interesting part. This minimization problem depends on the norm of L2 norm of z. Because for the first function, the input is the L2 norm. This term also depends on L2 norm. And this inner product term, it depends on z actually. So what we can do, we can equivalently rewrite this problem as follows. We can denote the L2 norm of z as alpha. We introduce it's like an auxiliary variable. We just denote this L2 norm as alpha. Okay. And then by definition, we can just put alpha, replace the L2 norm by alpha everywhere. And then previously we are minimizing over the vector z, but now by introducing this auxiliary variable, we are minimizing over alpha such that the L2 norm of z equals to alpha. These two are equivalent because in the first line, the minimization over z is unconstrained. We are considering all possible z's. Okay, and in the next line, we are minimizing over. There are two constraints here. The first one is that we are looking at the inner constraint. We are looking at all the z's such that their L2 norm equals to alpha. But this alpha can be anything bigger than or equal to 0. So this is actually considering all the z's, because so this includes every case about z. Because for any vector, the L2 norm is always bigger than or equal to 0. So there's essentially no constraint. This is just to rewrite the optimization problem in this way by introducing this auxiliary variable. Okay. Now the nice thing is that we can first, in this line, we can first look at the inner problem. In the inner minimization problem, we are fixing at the alpha. There are two levels of minimization problem here. The inner minimization is a fixed alpha. So we are looking at all the z's where the L2 norm equals to alpha. And then in the outer minimization, we further vary this alpha. Okay. So let's first consider the inner part. In the inner part, we are given this constraint. The L2 norm of z is equal to alpha. Okay, now I just so these terms are preserved. The last term is a constant, only depends on x, so it's preserved also. And so we only need to look at this inner product term. So essentially, we are minimizing over these z's of this negative inner product. So So we are considering this minimization problem. Right? Because given alpha, these two terms are fixed. The last term is also fixed. The only thing we are minimizing over is this inner product. And this is a very simple linear programming problem. We are looking for the we are looking for vector z with L2 norm alpha that has the maximum correlation with vector x. Right. So this is right, because I can ignore the negative sign but change minimum to maximization. Yeah. And here's the thing, we are maximizing over all possible alphas, all possible z's with a constant L2 norm. Now this is like considering all the vectors staying on the unit ball with radius alpha. And this is our constraint set. And the question is on this ball with radius alpha, what is the vector that has the maximum correlation with x? Right, suppose this is x. And it is clear we simply pick the z that has the same direction as x. Right, we simply pick this z. And this is given by the Cauchy-Schwarz inequality. So this one is less than equal to z L2 norm of z times L2 norm of x. And the maximum is achieved when that z aligns with x. So in this case, if we pick this z, then this is equality. So the maximum value of this inner product equals to the dot product of the L2 norm. Because when they are exactly aligned with each other, the angle is zero, so the dot product is simply the product of the norm. And in this case, it's alpha times x L2 norm. Right? Because we are given that L2 norm of z is alpha. So this shows that the maximization of this shows that this minimization of this negative inner product is negative alpha times, right? It's negative alpha times x, the L2 norm of x. Okay, so this is the solution to the inner minimization problem. Okay. Now, once we solve the inner minimization problem, then we consider the outer minimization problem. And then this line is simply minimizing over alpha bigger than or equal to 0. And the minimization is G alpha plus some quadratic terms in alpha plus a constant. So what we do is we can re we can put all these quadratic terms together into a square term. Okay, simple calculation. And then we just need to solve this minimization problem. And this minimization problem looks very close to the definition of proximal mapping. Optimal points. So let me check the original formulation. Yes, L2 norm. So this G function, yeah, so here, this G function, the domain of the G function is restricted to be positive because the input is a L2 norm, right? So it is not supported on the negative domain. Okay. Then this minimization problem is a standard definition of a proximal mapping associated with function G evaluated at L2 norm of X. Okay. Because this is minimizing over the entire domain of function G. So this problem, by definition, the minimizer alpha star, by definition, is the proximal mapping associated with G evaluated at this scalar value. So the minimizer to this problem is simply this proximal mapping. So this is the alpha star. This is the alpha star. This alpha star is what? Is this L2 norm of Z. Is the L2 norm of Z. So through this process, we have shown that for the inner minimization problem, the L2 norm of Z is fixed to be alpha, and moreover, the solution is when Z aligns with X, right? So now we have obtained the optimal alpha. Therefore, the optimal Z is simply this alpha star times a unit vector aligned with X. Because we just showed that the optimal solution for Z is the one that aligns with X. And now we have obtained the optimal L2 norm for Z. So this is the L2 norm of Z. And the question is, how do we create a vector that aligns with X and has L2 norm alpha star? Well, you simply scale this unit vector that aligns with X by alpha star. Right? So this vector will have L2 norm alpha star and aligns with X. And then you put everything together, alpha star is the proximal mapping. So this is our Z star. And the Z star is the minimizer to this original problem, which is by definition defined as the proximal mapping associated with F at X. Right. So this proves this claim. Yeah. And remember, when we talk about projection operators, we have this non-expansiveness property. Consider any 2 points x1 and x2, and consider their projection points onto the convex set C. And we have shown that the distance between the projected points is always smaller than or equal to the distance of the between the original 2 points. So this means that after projection, the distance will only be smaller. This is called non-expansiveness. We are not expanding. And then this projection operator is actually a special case of the proximal operator when the function h takes the form of an indicator function on a convex set. Okay. So therefore, we can extend this kind of property to the proximal mapping. So in fact, we can show for the proximal mapping, we can show the following two properties. The second one is what we is the one that generalized the previous property. It says that the proximal mapping is also non-expansive whenever h is a convex function. As long as this is convex function, then this mapping is also non-expansive. Now the first property is actually a stronger result than non-expansive, which we call the firmly non-expansive. So it shows that the difference between these two proximal points, okay, and this is a difference vector. This vector taking inner product with the difference of these 2 points is bigger than or equal to the square of the distance of these two proximal points. So the first bullet can imply the second bullet simply by Cauchy-Schwarz inequality. Therefore, the projection operator, right? If you replace h by the indicator function of a convex set, then this becomes projection, and then the first bullet will imply that even for the projection operator, the first inequality holds. So, which is a stronger condition than the non-expansive condition. So this firmly non-expansive implies this can imply non-expansive, but non-expansive cannot imply firm non-expansive. So this is because from firmly non-expansive, this is firmly non-expansive. This is firmly non-expansive. And then for this inner product term, I can further apply Cauchy-Schwarz inequality. Cauchy-Schwarz says that this inner product is less than or equal to the product of their norm. Right. And then I can cancel this with this one, which gives the non-expansiveness property. So from the first one, we can get to the second one, but not the other direction.
Why is firm non-expansiveness versus non-expansiveness? What conditions?
We showed that, okay, if we have firm non-expansive, then we always have non-expansive, because in this proof we only utilize Cauchy-Schwarz inequality, which holds for any arbitrary vector. So if we have firm, that's why we call it firm non-expansive. So it is a stronger condition. This can always imply the non-expansive.
Which type of equations would work with firm non-expansiveness, or which ones would you have to imply non-expansiveness? Is there?
Yeah, I guess here maybe to clarify, the specific assumption is that if H is a convex function, then the associated proximal mapping is firmly non-expansive.
Oh, I see.
And once we have firm non-expansive, we always have non-expansive property. Yeah. So as long as H is a proper convex function, we is a corresponding proximal mapping is always firmly non-expansive. We call this firm non-expansive operator. Okay. You can view this proximal as is a proximal operator that maps x1 to another point. Okay. So this shows that when we do proximal gradient descent, right, this mapping is actually kind of stable, because it is always reducing the distance in some sense. And this in this firm non-expansive property, okay, we can tell that because it says that this dot product is bigger than or equal to some positive number, but the right hand side is something positive, which means that after the proximal operation, this difference vector is still positively correlated with your previous vectors, with x1 minus x2. This means that when we do proximal gradient descent update, when we introduce this proximal update, it will not change the update direction that much. We will sort of still follow the previous direction, but here we will take into account this regularizer function h. Because when we do gradient descent, we are just performing a gradient descent on the differentiable function part, right? And then once we introduce this proximal mapping, this mapping will address that non-differentiable regularizer part. And this property shows that this proximal mapping is a well-behaved operator. It's a nonlinear operator, but it's well-behaved. Yeah, and we can prove this in a fairly easy way. Proof of fact 6.1. Yeah, so we can prove this fact. Let's see how. Let's look at the proof. So let us denote Z1, Z2 as the image of this proximal mapping. Proximal mapping at x1 Z1, x2 Z2. And then we have this subgradient characterization of Z1 and Z2. Okay, what does this? How do we get this? Let's say we denote Z1 as proximal mapping at x1, which means by definition is the arc mean Z 1/2 Z minus X squared plus H Z. Okay, by definition of the proximal mapping. And look at this optimization problem. H is a convex function, quadratic term strongly convex. So the entire problem is strongly convex. And by strong convexity, we know it has a unique minimizer. And that minimizer is what we define as Z1. And because it's the minimizer of convex function, we know that it satisfies the first order optimality condition. Basically, zero, the gradient at the optimizer is zero. Right? So we simply take the gradient of this part, which gives Z minus X plus. Now H may not be differentiable, so we use sub-differential instead. It's convex function. We use the sub-differential instead. This subgradient, okay. So zero must belongs to this subgradient at the optimizer. Look at this equation. This is the subgradient. Right. So this subgradient, this is the subgradient of this optimization problem. The subgradient at the minimizer Z1 must include zero, right? Because that's the first order optimality condition, necessary condition. You plug in Z equals to Z1 and rearrange the terms. You can get this result. So this is x1 actually. Okay. And then what you get is you move this part to the left hand side, you get x1 minus z1. This vector belongs to this vector x1 minus z1 belongs to the subdifferential of h at the minimizer z1. So this shows that Z1, that point, this point must satisfy this inclusion. This point must satisfy this inclusion equation just by optimality of this optimization problem. So we have this inclusion. And similarly for x2 and z2. Okay. And then we just need to prove the firmly non-expansive property. And then the non-expansive property follows from that, as we have we just proved that. Okay. And then this is the firmly non-expansive property that we want to prove. Because Z1, Z2, right, they are the proximal points. Right. If you go back to the firm non-expansive property, it says that the inner product between the difference of the proximal points and these 2 points, right, is bigger than the distance squared. So here Z1, Z2, they are these proximal points. Okay. So this is what we want to prove. And this equation, we can rearrange the terms. The right-hand side can be written as C1 minus C2 inner product with itself, right? So we can move the right-hand side to the left-hand side, combine these two terms. We can get this one. We can get this step. So this is what we want to show. Right? This is what we want to show. Okay. Now we will prove. Okay, so this is what we want to show. Okay, and we will prove this inequality by the following way. Because H is a convex function. So by convexity, we have HZ2 is greater than equal to HZ1 plus Z2 minus Z1 subdifferential of HZ1 by convexity. And we can switch Z1 and Z2. Just by convexity. H is convex function. So for n in 2 points, these inequalities follows. And then we have shown that for this subdifferential, right? So this x1 minus c1 is in this subdifferential. So I can plug in this vector into here. Yeah, because by convexity, this inequality holds for any point in this subdifferential by convexity. So we just showed that at this z1 point, it must satisfy this inclusion property. So I can plug in x1 minus z1 into here, and x2 minus z2 into here. And this gives me these two sets of inequalities where we plug in this subdifferential vectors. Right. Now okay. To summarize, for these two inequalities, we utilize two things. One is convexity of H. We assume H is convex function. The second thing is that we utilize this characterization of these proximal points. This is an equation that we will use many times. This shows that if Z1 is the proximal mapping of x1, then Z1 x1 must satisfy this inclusion property. Okay. So we use convexity and we use this optimality condition associated with the proximal mapping. So these two technical tools together gives us these two equations, these two inequalities. Okay. And then we simply sum them up. Now these function values will cancel with each other, and these two inner product terms, once we sum them up, they will give us exactly the above inequality. Okay, so this is proved by summing up these two inequalities. and then the firmly non-expansiveness is proved. With that, we can show the non-expansiveness. So this proves that some very interesting and very useful techniques where it's kind of we leverage the convexity of function and show some properties associated with their subdifferentials. You can see that even for the proximal mapping, from this proximal mapping, we can see that these points, they are related through this subdifferential inclusion equation. So the proximal mapping is related, this operator is related to the subdifferential operator in such a way. In fact, this inclusion equation, we can solve for Z1. We can solve for Z1. So what we have is Z if we rearrange these terms, move Z1 to the right-hand side, we have I plus subdifferential of H at Z1 contains X1. This is another nonlinear inclusion equation. It's the identity operator plus the subdifferential operator of H. The sum of these two operators act on Z1 will contain the point X1. And from this, we can derive that Z1 is actually the inverse of this operator applied to X1. Just move that operator to the right-hand side and take in the inverse. And we can show this inverse exists and is a unique mapping. The unique mapping. And you can see that this is another way to write proximal mappings. Right. Because here Z1 is defined by proximal H at X1. And this is a more explicit way to write this proximal mapping. It is the proximal mapping, it is actually the inverse of this operator applied to X1. And the inverse is the inverse of the identity operator plus the subdifferential of H. And we call this the resolvent operator, which we will introduce later when we talk about operators. For example, we are familiar with this. A matrix A, right? We sometimes we want to take inverse, but for those matrices who do not have a proper inverse, what we do, we usually add an identity, add a small diagonal elements to the diagonal parts of the matrix. And by doing that, it could be invertible. Here is the same thing, except the only difference is that matrix A is a linear operator. It's matrix times something is a linear transformation. But here we are talking about subdifferential operator, which is a highly nonlinear operator defined based on associated with nonlinear functions. But the idea is pretty much the same. This nonlinear operator may not be invertible directly, but once I add this identity, it could be inverted. It could be inverted. And turns out that the inverse of this operator can be written in such a nice proximal form. So this entire you see, this entire concept of proximal mapping is connected to projection, generalized projection, but also related to also generalizes linear operators. Yeah, and this is what we just discussed. That this mapping can be equivalently written as this inverse operator. Is the inverse of identity plus subdifferential of f, which we call the resolvent operator associated with f. Okay. And this operator is actually the core of modern optimization. We will see in the next several lectures that many algorithms starts from this point, and then we can derive the form of many complicated algorithms, operator splitting algorithms. Okay. So this operator is a one-to-one mapping because it is associated with this optimization problem. And this is a strongly convex problem. So for strongly convex functions, we know it has a single unique minimizer. Right? So the minimizer is unique, meaning that Z1 is always unique. So you see, if we ignore this identity, directly taking the inverse of this subdifferential may not exist. That inverse may not exist because that is corresponding to removing this quadratic term. Once you remove this quadratic term, and then we are directly looking at the minimizing of this h function. The function itself may have multiple minimizers, right? So that might be a multi-valued map. But once we introduce this quadratic term, which makes the function strongly convex, the solution to this problem is always unique. Right? So here in the operator form, this is equivalent to adding an identity operator, and that makes the operator invertible, immediately invertible. And we have just gone through this. You just write down the definition, optimization form of this proximal mapping. And since Z is the minimizer to that problem, so it must satisfy the first order optimality condition. So you just take subgradient. 0 must be in the subgradient at the minimizer. Take subgradient, this becomes subdifferential of f at z. And this quadratic term is differentiable, so we have z minus x. And then once we solve for z, we can get this equation. Yeah, and in fact, this mapping can be further used to characterize a lot of decomposition rules. For example, in the Okay. Anyway, so one concept that we are familiar in geometric analysis is that we can once we have a orthogonal basis, we can decompose any vector into two orthogonal parts. Right. And this happens in the Euclidean space where we talk about Euclidean geometries and possibly linear functions. It's like projection onto a linear subspace. But we can extend this idea to a nonlinear space by using the proximal mapping. Suppose f is a closed convex function, and we define this convex conjugate function f star x in this way. So we can this f star x may look a little bit complicated at this moment, but let's just accept this definition. The definition is that f star x is defined as, now given x, how do we define this f star function? Well, we first construct this function. It's an inner product of x between x and z and minus fz. And then I will take supremum over z. I look for the supremum value over all possible z's. This defines a function in x, because x is the given input, and then we are solving this problem over z. Suppose we can get the optimal z, we just plug it in, it will give us a certain value. Right? So this is how we define the conjugate function, and this function it depends on the f. F and f star, they form a primal dual conjugate pair. F is in the primal form, F conjugate is the dual form. Once we define this conjugate function, we can show that for any vector x, it can be decomposed in this way. X equals to proximal mapping associated with F, evaluated at x, plus the proximal mapping associated with F conjugate, evaluated at x. This equation is a very important and very nice, elegant equation that shows the relation between proximal mapping and the duality. And it also generalizes orthogonal decomposition. For example, if f is the indicator function of a subspace, then proximal f is the projection of x onto that subspace, right? And then we can show that f star is simply the indicator function of the orthogonal complement of that space. Okay. So this would be the projection operator onto the orthogonal complement subspace. So this covers that classic decomposition. You can project your x onto one subspace plus another subspace as long as they are orthogonal with each other.
The orthogonal complement subspace. So the diagram of projecting a vector into the x direction and the y direction to the right, that would be just like a two-dimensional version where the vector in the x direction is the orthogonal complement to the vector in the y direction. Is that what you're getting at?
Yes. So this is just a figure in 2 dimensions, but you can view, so you can write, so x is a high dimensional vector, and you can view the x-axis as one subspace, we can call it V, where the y-axis corresponds to V complement, the orthogonal complement of that subspace. Right? And we can project it. We can project any in linear algebra. Right? We can project any vector onto. We can decompose any vector onto two complementary orthogonal subspaces. Yeah, but that is done by projection onto a hyperplane, which is kind of flat, Euclidean. So I will not go over the proof of this theorem, but this equation is interesting even when we consider convex indicator function of convex sets. Right. This f may not necessarily be indicator function on a subspace. It could be an indicator function of a convex set. Then we are saying that, okay, I can decompose x by projecting x onto the convex set, which is the first term. Right? If I choose f to be the indicator function of a convex set, then x can be decomposed as first projecting onto a convex set, and then this proximal f conjugate is something related to another projection operator. Okay. And I think we have explanation here. Yeah. So let's consider an enclosed convex set. Okay. Now here's how we utilize this Moreau decomposition equation. So first, consider a convex set C, and we define the support function associated with the convex set as follows. This is a standard definition. So support function associated with C at X is defined as follows. So we are looking at the input X, right? So I fix X and look for this vector Z that has the highest correlation with X over the convex set C. Okay. The projection operator is looking for a point on the set that has the minimum distance, but this function is looking for the Z that achieves the maximum correlation over the entire convex set. So this is called the support function. Good. So the function value is the supremum value, the maximum correlation value that is achieved. Okay. So this is a function. It's a function that depends on your input X and depends on the given convex set C. Okay, and for this function, we can show that its proximal mapping is given as follows. The proximal mapping associated with this support function at X is simply X minus the projection onto C. For such a function, its proximal mapping has a very simple expression, which is simply X minus X subtracts the projected point onto C. So first of all, it is okay. Now we will prove this equation by leveraging that Moreau decomposition equation. First of all, we can show that the conjugate to this function is the indicator function. Okay, so let's first accept this this statement. Let's say the conjugate of this support function is actually the indicator function on the convex set C. Okay, since these two form a conjugate pair, we can apply that model decomposition. Because model decomposition is about F and this conjugate. Now I will set F to be that support function, and then this would be the conjugate of the support function. Okay, and then I simply apply the model decomposition. Model decomposition says that X equals to the proximal mapping associated with this function plus the proximal mapping associated with its conjugate. But we are given that the conjugate is the indicator function. And the proximal mapping associated with the indicator function is simply the projection operator. So this proves that the proximal mapping associated with the support function is given by this form. Okay, and this actually gives a very elegant decomposition for arbitrary projection operators on convex sets. So it says that any vector X can be written by the projecting it onto any convex set plus the proximal operator associated with the support function. This is a general nonlinear decomposition. And it generalizes this orthogonal decomposition that we are familiar with. In this orthogonal decomposition, the convex C is maybe it's a linear subspace, and then the proximal associated with the support function would be the projection onto the orthogonal complement. Okay. But in this equation, this C may not necessarily be a subspace. It could be an arbitrary convex function. And utilizing and this, based on this result, based on this this equation, we can look at some examples. We can derive the proximal operator associated with some norms. For example, we can show that the proximal operator associated with the L infinity norm is given by this. It's given by X minus projection onto the unit L1 norm ball. Okay. So this proximal operator is related to this X minus projection onto the L1 norm ball. Right? So if you want to introduce the L infinity norm as the regularizer and apply proximal gradient descent, right, you will need to compute this proximal operator. And to prove this equation, we observe that the L infinity norm has such a variational form. This is by the duality between L1 and L infinity. Right? So you can check the maximum entry, right? The entry with the maximum magnitude, that is the L infinity norm, right? Is defined to be the supremum of this inner product, well, the supremum is taking over all the z's with L1 norm less than 1. Okay. Why? Because it's very simple to intuitively see this. Let's say X has the largest magnitude. The entry with the largest magnitude is in the ith coordinate. And I simply, for that coordinate, I can design the supremum of Z will be achieved by a standard vector, right? With 1 in the ith coordinate and 0 everywhere else. So that Z would achieve the maximum value. So it is characterized in this variational form. And this is simply, by definition, the support function associated with the L1 unit ball evaluated at X. If you compare this with the definition of the support function. Now this set C becomes this L1 ball. So it's a support function. Therefore, we can leverage that the result in the previous slides. So the proximal operator is basically the proximal operator associated with this support function. And therefore, it's given by X minus the projection onto the L1 ball. And then this term can be computed using some other algorithms efficiently. Projection onto the L1 ball. Yeah, this example is that define this function gx, which takes the maximum value among all the coordinates. This is not the L infinity norm, because L infinity norm is the maximum value among the absolute value of all the coordinates. Here we are not, there's no absolute values here. It's simply a maximum value among all the coordinates. Then the proximal mapping of this function is given by X minus projection of X onto the probability simplex set. And this is proved by observe that such a G function is simply the support function associated with the simplex, probability simplex. With this claim, with this given result, right, the proximal of G is the proximal of this support function, which is given by X minus the projection onto this simplex set. And this is actually a highly nonlinear function because it contains many linear segments, and it is not differentiable. But the proximal mapping has a very simple form. Okay, so these are everything about the proximal mapping. Yeah, this Moreau decomposition. So many theories on this, many operator theories and convex optimization theories are developed based on this conjugate function and this Moreau decomposition. Yeah, and it is not hard to verify this small claim. The conjugate of this support function is the indicator function. Now maybe we can follow the definition of conjugate function to we can quickly do this as a practice, but just follow this conjugate definition. The conjugate of f is defined as sup over z inner product z x minus right. It's the inner product minus the function evaluated at z. Well, this function is your original function, but that does not have a star in it. Right, and this is the expression. Now our function is the support function. And then let's just write it more explicitly, write it out. Now the support function, what is the support function? The support function is, and again, given by such a variational form. So let's just write it down. Okay, now we need to be careful, pay attention to the notation. Here is xc evaluated at x. Here we are evaluating at z. And I'm going to, for this z, I'm going to use another notation, maybe t. Right. So this sup is the support function of c evaluated at z. And then what do we do? Yeah, I can do this. Sup, I can I can make it inf. Yeah, because I pull it out of this negative sign, so sup becomes inf. And the first term is a constant because here I'm taking the supremum over t, and this term does not depend on t, so it's a constant. Doesn't matter. So this becomes cx minus t. Right, so I have a supremum over z, infimum over t, and I think yeah, I think in this case we can swap this supremum and infimum by the duality, and then I need to I probably need to think about this more carefully.
Sorry to interrupt, but yeah, I'm still a little bit confused on what the support function is in the bigger picture of using these optimization algorithms.
Yeah. So So we're out of time. But I think
So its support function is looking for the vector z that has the maximum correlation with x in the convex sets.
in the convex set, right? So
But what actually is in the sum of the vector x equals z? So I mean, it's optimizing x.
yeah, if C is a linear subspace, right? We can quickly answer this. If C is a subspace, then so I'm looking for, and let's say X is this vector. X is such a vector, and then I'm looking for the vector that has the highest correlation in this set. So maybe you want to project X onto this space, and then so this projected vector is the vector that you want to go for, right? So basically you are looking for the vector in C that aligns with this projection.
Yeah, that makes sense.
Yeah, and it's, for example, if C is a it's a bounded ball, maybe a surface, then you are looking for all the vectors. Yeah, I think it is the vector that aligns with this projected vector. But if this C is not a subspace, then things could be more complicated.
Just to be clear, z would be the vector like the bottom of the triangle.
Yeah, then this would be Z. This vector or the vectors along this direction will have the highest correlation with X. Okay, maybe so let's stop here, and maybe next time we will go back to this part again, and maybe check how we derive this conjugate and how to understand this support functions.
Thank you.
Okay, thank you guys. And by the way, the next Thursday we will cancel